Modern computing is built on a strict linear flow. In a standard logic architecture, data moves from inputs through a computational gate to produce a single deterministic output. This rigid model encounters immediate roadblocks in asynchronous networks or constraint satisfaction problems. If an output is known but an input is missing, classical logic gates cannot attempt to reverse their computational flow. They hit a bottleneck and fail. To function effectively, distributed intelligence networks require a logic unit capable of absolute structural reversibility. This is the operational specification of the Trigate. The Trigate serves as the minimal ternary resolution unit, engineered specifically for the transcender distributed reasoning system. It abandons unidirectional calculation entirely. Instead, the Trigate operates as a multidirectional constraint matrix connecting 5 distinct variables. Its core operation relies on mathematical set reduction. Rather than assigning an absolute fixed value to a variable, the Trigate continuously narrows down the domain of possible answers. When this reduction encounters a dead end, the unit structurally reframes logical contradictions, turning them from terminal system failures into active routing signals. A genuinely distributed intelligence requires logic gates designed to fail gracefully, keeping the system online while autonomously requesting contextual help from the surrounding graph. The Trigate operates strictly within a ternary domain, consisting of 0, 1, and 2. In this specification, 2 is explicitly defined as unknown. The value 2 does not represent a fractional truth state. It specifically denotes an open, unresolved domain where closure has not yet been achieved. Variables within the Trigate do not hold single assigned values. They function as mathematical sets, containers holding a range of valid possibilities. A fully open variable contains 0, 1, and 2 simultaneously. A closed variable has been restricted entirely to a single integer. Resolution begins by reading input domains and generating a temporary compatible set. Under the intersection invariant, the target variable physically shrinks to the strict mathematical overlap. This yields a critical rule. A Trigate strictly reduces domains, it never expands. In an asynchronous system operating without a central clock, this strict one-way reduction is the exact mathematical mechanism that guarantees network stability and prevents chaotic data oscillation. To execute these reductions, the unit relies on 5 operating variables: inputs A and B, logical mode M, result R, and the control variable C. The control variable C acts as an orientable switch dictating the active target. When C equals 1, inference, flow converges to restrict result R. At C equals 2, deduction, flow reverses backward to restrict input B. Finally, at C equals 0, learning, it deduces mode M. Regardless of which C mode is active, the internal mathematical rules governing the Trigate remain completely unchanged. Decoupling logic from directional flow allows a single element to perform inference, deduction, and learning, operations that historically required entirely separate hardware. As domains restrict, the system evaluates its logical quality using an internal tracking metric called the coherence state, labeled E. A domain narrowed to a single value sets E to 1. If mathematically ambiguous, E equals 0. Crucially, if intersection yields an entirely empty set with no logical overlap, the metric registers a contradiction at state E equals 2. A standard architecture halts at an empty set, causing cascade failure. The Trigate prevents this by a semantic decoupling. It masks the empty domain by projecting an operational value of 2 outward, silently preserving its internal core as E equals 2. Exporting that protective value of 2 allows the global graph to continue computing smoothly around the impasse. Both an open domain and a contradiction project a visible 2, but their internals differ. One lacks information, the other is a mathematical conflict. By internally preserving that contradiction, the E equals 2 state functions as a structural beacon. It actively requests alternative data and contextual redundancy from neighboring nodes. In a functional distributed system, contradiction must be resolved by broader context, not by silently erasing the error. Expanding our view reveals the macro architecture of the transcender system. It is an immense web of interconnected geometric nodes, pulsing asynchronously without a master clock. To function correctly without a central rhythm, the network relies on an event subscription model. Trigates rest quietly, reacting only where one of their specifically connected variables registers a change. This propagation is governed strictly by the anti-loop rule. A trigate is explicitly forbidden from emitting an event unless its operation physically shrinks an internal domain set. This requirement starves out infinite logic loops, ceasing propagation when sets hit maximum mathematical reduction. To monitor the effectiveness of these pathways, the system relies on a final metric, f. This metric tracks the directional evolution of coherence, measuring strictly whether a specific operation improved, maintained, or worsened the local state. Metric f is not a guarantee of global system convergence. It operates purely as a local historical indicator, allowing the surrounding network to learn which routing pathways provide the most reliable data corrections over time. This model breaks from traditional Boolean computing. Logical resolution is no longer defined as the calculation of absolute 6 truths, but as the navigation of reversible domain restrictions. By decoupling operational values from internal coherent states and weaponizing logical contradictions as active routing signals, the Trigate establishes the minimum viable architecture required for true decentralized reasoning.